Okay, good to go. Today we're just going to wrap up 2.5, which is on continuity, right? So we started continuity last day and decided that, well, the idea of continuity is kind of, well, intuitive, right? If we've got a function, then it's continuous if there are no breaks or asymptotes or anything like that, right? And so thinking of a continuous function is not that bad, right? Especially if we've got a graph, we can say if it's continuous right away. The tricky part is deciding if a function's continuous mathematically, right? And proving that it's continuous and being able to use the properties of continuity. And so today we're doing 2.5 on continuity continued, and we'll hopefully be able to wrap it up. I think so. So we'll start with a kind of a theorem here. So if f is continuous at b, and the limit as x approaches a of g of x is equal to b. So if f is continuous at the point b and the limit of g is b at some point a, right? Then we can say that the limit as x approaches a of f at g of x is f of b. Now that's kind of, if you just kind of think about it, right? That's reasonable to say the limit at a of g was b, and so now, and also f was continuous at b, so of course then the limit at a is f of b. So that is to say that the limit as x approaches a of f of g of x is the same as f of the limit as x approaches a of g of x. Yep.
Can you give us like more examples for better understanding, like as we do after we look at the theory, and after that you give a question that we solve in the class. Like, can you give like 2 or 3 instead, so that?
I wish I could, but there's no time.
No, as like you can give us like these are the questions which are relevant to this one, so that we may be able to be practice for that.
Yeah. To do on your own?
Yeah. But like as in pre-calc, I did like our professor, she used to give us like formula, and then she used to teach us all the questions rather than theory, because like with that we are more practiced as comparative to theory, because we listen to this theory but we never go through again, and for the sums we go again and again.
So the problem with this course, so the question is, can we do more examples, essentially? I wish we could, but there's no time. Because, so the reason we have to talk about all these things, even though they seem kind of disconnected, is that we need to have this kind of toolkit, I guess, of facts that we can draw from, right? And so I wish we had more time to just sit and do examples and examples and examples. And that's what the WebAssign is for, right? So you can go and sit and do more problems, more questions. You've got access to the textbook, right? And so you can find similar questions. I tried to pick examples that'll kind of lead you through problems that are similar to what you have to do, right? But as far as more examples, we just don't have time to do them. Okay? So here, right, how are we going to use this fact, right? So I give you facts, right? And then it's your job to kind of string them together to make kind of a whole, right? And I do my best to kind of guide you through that. So what does this say here? If we have a continuous function, right, and we're taking the limit of another function, and we know the value at that point, and that point is in f, then the limit essentially passes through continuous functions, right? And so we've got this kind of, okay, well, if we have a continuous function, right, which we saw polynomials are continuous, right? And so then if we know the value at that point, then we can just plug it in, and then we go from there, right? And so, yeah, anyways. So, yeah, a lot of theory, okay? But that's calculus, right? Well, it's math, right? It's just math. So, anyways, threw me for a loop here. So what's that to say? That limits, oops, sorry. Limits pass through, sorry, I get so jittery, throws me off. Pass through and too much coffee. Continuous functions. Oops. Thanks. I'll have to clean that up. Anyways. The limit as x approaches 1 of arc sine of 1 minus root x over 1 minus x. Okay. Arc sine, right? We established in chapter 1, arc sine is continuous between 1 and -1, right? Inclusive. And so knowing that arc sine is continuous on this point, and we're interested as x approaches 1, right? Then we know that this limit is going to exist, right? And so we know arc sine is continuous on the interval -1 to 1. So if arc sine is continuous at the point that we're interested in, then we can pull that limit inside, right? Which we can take the limit of 1 minus root x over 1 minus x. We can do that, right? And then we can take the arc sine of that limit. So we can rewrite this. The limit as x approaches 1 of arc sine of 1 minus root x over 1 minus x, just rewriting the problem here, is the same as arc sine of the limit as x approaches 1, oops, of 1 minus root x over 1 minus x. So if we just focus on the limit inside then, right, limit as x approaches 1, of course, you're dealing with dividing by 0. You know you're not allowed to do that, so we can't just plug it in, right? But we know that we can manipulate this into something that we can find, right? Essentially, we've got two options here. My first thought was, well, I could rationalize the numerator, right? Or another option is to factor out the denominator. Right, so you've got two options here. Either way, you're trying to avoid dividing by 0, right? And so we've got the arc sign on the outside. That stays the same. But we want to take the limit as x approaches 1. And I can show you both ways. Right. 1 minus root x over 1 minus root x times 1 plus root x. I'd call this option 1. Factor the denominator. Option 2, oops. Or you can do the arc sign of the limit as x approaches 1 of 1 minus root x over 1 minus x times, oops, 1 plus root x over 1 plus root x. Or option 2, rationalize the numerator, which is kind of my go-to, I would say. But that's just personal preference, I guess. So as soon as I see a 1 minus root x, or as soon as I see a root plus or minus a number, or a number plus minus a root, I just kind of go and rationalize, because that's usually how I'm going to be able to not divide by 0 anymore. And either way, if we work through this, I don't know which one you want to stick with. Because the option 1 is kind of more obvious, right? Then we cancel the 1 minus root x with the 1 minus root x. So there's nothing really left to do there. So it is quicker, right? Because then we can just plug in. So then we have 1 over 1 plus root x as x approaches 1. We get 1 over 2, right? So that's easier to see. But if we keep going with this rationalizing the numerator, take the arc sign, the limit as x approaches 1. 1 times 1 plus root x minus root x minus x over, right? Make sure you treat these as their own things. 1 times 1 plus root x minus x, and then minus x root x. This becomes the arc sign of the limit as x approaches 1 of 1 minus x. Right? We cancel out. And then we get I can do some stuff, right? I can kind of rearrange. I can pull out a common x from some of these. And so I have 1 plus root x, and then minus x times 1 plus root x. now I've got a term of 1 plus root x, and then x times 1 plus root x. So then we're taking the arc sine of the limit as x approaches 1 of 1 minus x over, and then 1 plus root x. Oops, jumped around. Times 1 minus x. Right. Now these cancel. And again, I'm just left with 1 over 1 plus root x. And now I'm able to plug it in, plug in x equals 1, and so I take the arc sine of, whoops, 1 over 1 plus root 1, which is the arc sine of 1 over 2. Okay. So either you've got a fun calculator, like this one that just tells you it's pi over 6. Right? I think the engineering calculators can just give you exact answers. And so, so that's nice. Or you have to go and remember the unit circle. Oh man, no one likes that. Maybe this isn't sounding like such a bad investment after all. One that just tells you it's pi over 6. But try your calculator, right? Especially these ones, which are pretty common. Does it default to giving you exact answers, or do you have to tell it to give you exact answers? So if you take the inverse sine of 1 over 2, yeah. Oh, put it in radians. It should be their setup. Oh yeah, setup. And 4. Try again. So we could remember this little guy. Right. That's nice, right? Or we could remember this little guy. Okay. Because if we know, okay, so arc sine is the inverse sine. Oops, that doesn't make sense. Arc sine of x is the same as the inverse sine of x, right? And so since the sine of pi over 6 is equal to 1/2, right? Our answer to the inverse sine, right, is going to be pi of 1/2 is pi over 6. So the inverse sine of 1/2 is pi over 6. Right? And so we're here. And I'll just say, make sure you are in degree mode, or sorry, radians. Radian mode. Basically, for the rest of the course, we're going to be in radians, most common. Okay. Okay. What we said, right, is that limits pass through continuous functions. And so we can extend that to kind of the function composition, right? F composed with G. And so if G is continuous at A and F is continuous at G of A, then the composite function F composed with G, right, given by F composed with G of X, which is the same as F of G of X. So usually when I'm reading the function compositions, right, I just read the little O as of, because it's the same, right? So F of G of X is continuous at A. What's this saying? A continuous function of a continuous function is a continuous function. That's not that crazy, right? But it all hinges on it being continuous. So a continuous function of a continuous function is continuous. For example, if I ask you, where is h of x equal to the sine of x squared continuous? You can break this down into a function composition, right, and figure out, well, if the first one's continuous and then the second one's continuous, then the composition of the two is going to be continuous, right? And so if we let h of x be f of g of x, where f of x is the sine of x and g of x is x squared, we know g of x is continuous. We know g of x equal to x squared is continuous on the set of real numbers. And f of x equals sine x is also continuous on the set of real numbers. If there had been a restriction, right, then the composition of the two, right, it would just be continuous on the overlapping part. Right? In this case, we're good to go on both fronts, and so therefore h of x equals f of g of x is continuous on the set of real numbers. let's talk about the intermediate value theorem. Suppose that f is continuous on the closed interval, on the closed interval a to b. So it doesn't have to be continuous everywhere, just continuous on this interval. Okay. And let capital N be any number between f of A and f of B. Where, of course, f of A can't be equal to f of B because then there would be no space in between them, right, for N to B. Then there exists a number, bless you, C, in AB, not necessarily inclusive, right? Such that f of C is equal to N. This is a biggie. So I'm going to put 2 frames around this one. Again, pretty intuitive stuff, right? If a function is continuous between 2 points, then there must exist a point between those 2 values of x, right, in that interval that is going to yield some value n, right? And so if I know 2 points and this function is continuous, I can pick a point in between and there exists some output n because it's continuous. Okay. And so here, I'll put note. There can be more than one C that yields n. There can be more than one C, oops, such that f of C equals n. For example, if we just have the 1, then between A and B, on the closed interval between A and B, here, let's just say the function looks like this. Something like that. Yeah. All the intermediate value theorem is saying is that, well, then there exists some C, right? If I pick a value of n here, between f of A and f of B, right? Here's f of A and f of B. If I have some value of n between f of A and f of B, then there exists some C that makes that happen between A and B. You can even have multiples, right? Like we said, multiple C's that make that happen. That's if you have something that looks like maybe like this, where this is A and this is B. Because now, here I am at f of a, and here I am at f of b. If I pick some value of n between those 2 points, right, then there's actually 3 values of c that make that happen. C1, C2, C3. Right. So here we've shown that f of c equals n. Here f of c1 equals n, f of c2 equals n, and f of c3 also equals n, right? So we found more than one point that yields an n, right? So that can happen too. How are we going to use this? Oops, too far. If I want to know whether a function, a continuous function, crosses the x-axis, right? Usually we call those solutions, right? Or roots, right? If we want to find if there are any roots, then that's usually the most common way that we use this theorem is we say, well, if I'm able to plug in values into this function and get a negative value and a positive value, then the intermediate value theorem tells me that at some point between these 2 points, I don't really care where, it's going to have to equal 0, right? I've got negative on one end and a positive on the other end. Even if it's the other way around, right? It's crossed 0 at some point. And so that's how we're going to use it. And so the application here is showing that an equation has at least one solution. Has at least one solution. So if you have to show that there is a root, of the equation four x to the power of 3 minus 6x squared plus 3x minus 2 equals 0. Right? So here I want to show that there exists some x that makes this 0 between 1 and 2, right? Narrowing it down. Okay. To reword it, right? Show that there is at least one solution between x equals 1 and x equals 2. Show that there is at least one solution between x equals 1 and x equals 2. First thing I'm going to do is I'm just going to look at the expression, right? So this polynomial, so I'm going to let, just so I can talk about it easily, let f of x equal 4x to the 3 minus 6x squared plus 3x minus 2. Just so I can talk about f of x like I did in the intermediate value theorem. And so we know f of x is continuous on all values of x, right? Because it's a polynomial, so we know that it's one of those functions that are going to be continuous. And so it's definitely continuous between 1 and 2. Right? So we know f of x is continuous on the interval 1, 2 inclusive because it is a polynomial. So what can I do? Well, if I'm given points, I may as well use them, right? And see, okay, well, if I have to show that there is a solution, then I can just plug in a equals 1, b equals 2, figure out what those values are of f of a and f of b, right? And then if 0 is between those values, then there must exist some value between 1 and 2 that makes that happen. And so we can find f of 1 is 4 times 1 to the power of 3 minus 6 times 1 squared plus 3 times 1 minus 2. Four minus 6 plus 3 minus 2. I get -1. Now what I'm hoping for is that f of 2 is going to be positive, and then I'm in the clear. So f of 2 is 4 times 2 to the power of 3 minus 6 times 2 to the power of 2 plus 3 times 2 minus 2, which is 32 minus 24 plus 6 minus 2, which is 12. Phew. All right. So no matter what this thing looks like, right, at some point to get from -1 to 12, we had to cross the point 0, right? And so between 1 and 2, there exists some value. We don't really know or care what it is, right? That's going to give the solution. And so put it on the next page. Since n equals 0 is between f of 1 equals -1 and f of 2 equals 12, there exists a c in the interval 1, 2, not necessarily inclusive, right? Such that f of c equals 0, right, as desired by the intermediate value theorem, which we'll abbreviate IVT. Maybe I'll go up and put it in our little box here. So that was an interval where I gave you, okay, you have to show me that there is a solution to this problem, right, between these 2 points. It can be a little bit more open-ended than that, right? And so another example, if we have to show that cos x equals x to the 3 has at least one solution, right? So I'm not saying how many, but has at least one solution. first thing I'm going to do is I'm going to rewrite this. I can subtract x to the 3 from both sides, right, and get it in terms of equal to 0, because that's what that's going to be the easiest thing to work with, right? If you set your function, or you find a function and set it equal to 0, then all you have to do is find a negative value and a positive value, or the other way around, and then you know that 0 is between those 2 points, right? And so we can write that cos x minus x to the 3 equals 0. And then same thing, just so we can talk about it, let f of x be that function cos x minus x to the 3. We know that cos x is continuous for all values, all real numbers, and then x to the 3 is also continuous on all real numbers. And so subtracting one continuous function from another, we just get another continuous function. And so we know f of x is continuous on R, continuous on the set of real numbers. So we pick an interval, any interval a, b, by trial and error, right? There's no science to this. We just start with numbers and pick our numbers, and usually we kind of work our way closer and closer if we're interested in the solution. Here we just want to find a solution, right? And so we pick an interval a, b by trial and error. Trying to find an interval where f of a and f of b are on opposite sides of 0, right? It doesn't matter which one's positive and which one's negative, right? Either way, it would have to, at some point, cross 0. If we let a equal 0 and b equal pi over 2, right? Mostly because we're dealing with that cosine. But you can work your way through it, right? It's going to be easier if you kind of use pi over 2 or pi or some sort of radians for that cos x, right? But I mean, you could plug in 1, why not? And then we would find that f of 0 is cos of 0, which is 1, minus 0 to the power of 3, so we just get 1. F of pi over 2 is cos of pi over 2, which is 0, minus pi over 2 to the power of 3. Now we get 0 minus pi to the 3 over 2 to the power of 3 is 8. 0 minus something puts me at a negative number, and so I get negative pi to the 3 over 8. Therefore, f of pi over 2, right, is less than 0 because it's negative, and then f of 0 is greater than 0 because it was positive. On the closed interval 0 to pi over 2. Oops. by the intermediate value theorem, there exists a C in the interval, sorry, the open interval 0 to pi over 2, such that f of C equals 0. So that's why we can say that there's at least one solution, right? We could probably potentially find more with the cosec's, right? But so we can say that cos x equals x to the 3 has at least one solution. Any questions? No? So that's 2.5 wrapped up. Intermediate value theorem being the moneymaker in there, right? And so we'll do 2.6, so maybe 2.7 for next day. See you then. Oh, and as soon as your tests are marked, I'll just post your marks on Moodle. Okay. Of course.